Welcome everyone to today's session. I am excited to introduce you to Swift Firefly, a project designed as a cross-language learning experiment. This initiative explores the fascinating intersection of Zig, WebAssembly, and Swift, demonstrating how these three powerful technologies can be integrated to build modern, high-performance applications. Let's dive into the details of this experimental journey. This project demonstrates a macOS desktop overlay that renders animated fireflies floating above the user's wallpaper. On the left, you can see the intended visual result, which creates an atmospheric effect across the desktop interface. The engine driving this application, shown on the right, relies on complex interop logic to bridge the underlying system calls with the high-level rendering. While functional, this project is primarily a learning experiment and is not intended for production environments. The motivation behind this architecture is rooted in three primary objectives. First, we are examining the path from Zig to WebAssembly, specifically investigating whether Zig can generate small, efficient modules that avoid heavy runtime overhead. Second, we are assessing the integration of Swift and WebAssembly by testing the performance of WasamKit for real-time 60 frames per second applications. Finally, the cross-platform potential is a significant factor. By writing the core logic once in Zig, we create the possibility for the code to run across various environments, including modern web browsers. The architecture stack is organized into three distinct layers to ensure optimal performance and modularity. At the top, the Swift host handles platform-specific duties, specifically window management and the rendering layer. Below this, WasamKit serves as the essential intermediary, providing the runtime bridge and managing module loading. Finally, at the base of the stack is the Zig module. This is where the core application logic resides, including all math, physics, and state management. As the arrow indicates, the flow of execution moves from the top down, with function calls originating in the Swift host and being passed through the WasamKit bridge to interact with the high-performance Zig core. The core logic of the system is implemented in Zig, prioritizing performance and efficiency. State management is handled by Firefly.zig, which serves as the central hub for the system's operational state. Our math and physics layer consists of two specialized files: Bezier.zig, used for defining cubic curve paths, and Vec2.zig, which provides fundamental vector operations. For generating random sequences, we use Random.zig, which features a custom implementation of the XOR-Shift64 pseudo-random number generator. Despite these comprehensive features, the entire core logic compiles to an exceptionally small binary size of approximately 7.7 kilobytes. The host application is built using Swift and serves as the essential environment for the system. It handles four key responsibilities. First is lifecycle management, which occurs in app.swift. This is where the overall macOS application state is maintained. Second is rendering, handled within fireflyview.swift, where we utilize core graphics to draw the visual output. Third is timing, where we utilize CV_DisplayLink to drive the frame loop, ensuring perfect synchronization with the display. Finally, the host is responsible for loading, specifically ingesting the .wasm binary to integrate the core logic into the application environment. WasamKit serves as the essential bridge between the Swift host environment and the WebAssembly module. In this architecture, the Swift host functions as the active driver. This is a crucial distinction, as it means the WASM module remains passive. It contains logic and data, but does not execute on its own. Instead, Swift initiates the process by loading the module via wasmbridge.swift and then explicitly executes functions as required. This ensures that the host maintains full control over when and how the WebAssembly code is utilized within the application's workflow. The data flow and interop loop illustrates the synchronized lifecycle of a single frame between our Swift host and the Zig-powered WebAssembly core. The process begins at the top, where Swift requests a frame to initiate a new update cycle. In the second stage, Swift invokes the WASM update function, passing the elapsed delta time as a parameter. This transitions control to the third stage, where Zig performs the high-performance calculations required to determine new positions and update the simulation state. Finally, the loop concludes as Swift reads these updates directly from shared memory and renders the frame to the screen. This architecture allows us to leverage Zig's computational efficiency while maintaining a responsive, native user interface. Moving on to the exported WebAssembly API, these functions serve as the primary bridge between the JavaScript host and our simulation module. First, WASM init establishes the simulation state by taking the initial entity count, a random seed, and the viewport dimensions. The WASM update function is called within the animation loop to advance the simulation by a specific time delta in milliseconds. To facilitate efficient data transfer, we use WASM get Firefly count to retrieve the current number of active entities and WASM get positions PTR to obtain a direct pointer to the memory buffer where position data is stored. This allows the host to read simulation data directly from the WebAssembly linear memory. Finally, WASM resize allows us to dynamically update the simulation boundaries in response to window resize events, ensuring the fireflies remain constrained within the visible area. This slide illustrates the shared memory layout designed for maximum efficiency. The data is stored in a raw, flat array of floats, where each triplet consists of x and y coordinates, followed by a b value representing brightness or opacity. Swift accesses this information directly via a pointer, which allows for high-speed reading without any serialization overhead. By avoiding the need to transform or copy data between different layers, we significantly reduce latency and maintain optimal performance. The project structure for Swift Firefly is designed with a clean separation of concerns. The SRC directory contains the portable Zig logic, including the core engine in firefly.zig and specialized utilities in Bezier.zig. This ensures the foundational logic remains decoupled from the host environment. Conversely, the Swift directory houses the platform-specific host code, featuring the main application entry point and a WASM bridge to facilitate communication between the Swift frontend and the Zig backend. At the root level, build.zig manages the Zig compilation process, while the task file handles automation for various development workflows. This architecture maintains a clear boundary between core functionality and platform implementation. Moving into the project requirements and current statistics, you will need to be running macOS 14.0 or later. For the development environment, we require Zig version 0.15 or higher and Swift version 5.9 or above. While Task is considered optional, it is available to assist with common development workflows. Looking at the language distribution of the codebase, Zig represents 61.3% of the project, while Swift makes up the remaining 38.7%. To get started with the project, you can use the automated command task run app. This script streamlines the entire workflow by building the WebAssembly module, copying the resulting binary to the appropriate directory, and launching the Swift application. If you prefer to perform these steps manually, start by running zig build with the release equals small flag to compile the code. Next, copy the firefly.wasm binary from the Zig out folder into the Swift Applications Resources directory. Finally, navigate into the Firefly app directory and execute Swift run to start the application. Turning to our future goals and limitations, let's start with the reality of our development. While our current path is promising, a pure Metal and Swift version would ultimately be more practical for a production-level screensaver. However, we have found a major opportunity in that the core logic is now fully portable. This allows the same WebAssembly module to be dropped directly into a web browser, significantly expanding its potential use cases. Currently, our status is strictly experimental, as this project remains a proof of concept only. The key takeaway from this project is the successful demonstration that low-level simulation logic, authored in Zig, can be made highly portable through WebAssembly. Crucially, this portable logic can be driven with high efficiency by native, high-level applications written in Swift. This proves a viable pathway for cross-platform, high-performance simulation kernels integrated into modern native ecosystems. For those interested in exploring the implementation details, the complete repository is available on GitHub under Pastel Sketchbook /Swift Firefly.